The Thermo-Electric engine, the engine of choice on Kondaru and CogMap 2. The TEG, as we'll call it from now on, takes thermal energy and turns it into electrical energy for the station. Two different gas loops are on either side of the TEG, a hot loop where gas will be heated, and a cold loop where gas will be cooled. Both loops are connected to a gas circulator, more commonly referred to as a blower, on each side of the TEG. These blowers intake the gas and circulate it in, letting them interact for a bit, and then back into the loops. At the center, a thermocouple takes the thermal energy created by the two gases transferring heat to each other and turns it into electricity. The hot loop's gas will need to be reheated, and the cold loop's gas recooled as they both equalize each other, transferring their heat with a thermocouple. At the hot loop, you have a few options for heating the gas. The safer and simpler option is using charcoal in a line of furnaces. You may hear people refer to this as a char burn or furnace burn. The furnaces simply heat up to 3200 Kelvin and transfer the heat into the hot loop. The more experimental but often more rewarding option is to use the combustion/burn chamber, usually referred to as a chamber burn. The burn chamber takes a mixture of chosen gases and fills the burn chamber with it. The mix is almost always some combination of plasma and oxygen, but alternative gases can be added in for different effects. This mixture can be tailored with the gas mixer control terminal. Whenever you're ready for the chamber to be used, press the ignition button and let the gas heat up enough to be used for the engine. Use the vent to empty out the gas chamber into space, and use the heat shield if the mixture becomes too hot for the plasma glass to contain without melting your face off. At the cold loop, there are two methods of cooling. The first one, needing no setup at all, is the space radiators. All it is simply letting gas spend some time in the space pipes, cooling it down up to 2.7 Kelvin in the process. The alternative is gas freezers, somewhat equivalent to the hot loop's furnaces. Gas blowers simply work to cool gases to the target temperature on them, to a minimum of about 73 Kelvin. These should be turned on if the space isn't keeping the cold loop cold enough. Take note of the pathing of the gases. Various valves need to be opened in order for the gas to flow through the loop properly. In addition to each gas connecting to their respective blower, there are auxiliary valves handy to keep in mind. Purge valves vent out any gas inside the loop into space, which is very useful for emergencies or resets. There are also options for auxiliary tanks, increasing the volume of the whole loop, and taking some pressure off the pipes whilst not affecting other variables like temperature. If at any point you want to inspect how your TEG is running, you can either use the reactor statistics computer to get a thorough rundown of some vital statistics of the TEG and combustion chamber, or use the gas meters or an atmospheric analyzer to monitor pipe pressure and gas temperature. There's some indicators on the TEG as well to display how it's performing. The screen will display a general indicator of the power output, and all clicking it will give the actual number. If it's a low, yellow, or red bar, it means that the engine is predicting that it will be unable to perform in 5 minutes or 1 minute respectively. The math on it is a little shoddy, but it's still a good visual indicator the engine has something wrong with it, or it's just getting warmed up. If it's anything else, it's just a visual indicator of how much power is being made. The engine will make a lot of warning noises and dangerous lights, but these, surprisingly, aren't anything to worry about. Despite all the flashing lights as such, the TEG doesn't really break or have a maximum amount of energy it can dish out. Even if the engine is exploding or electrocuting everything nearby, the engine's actually just fine. Keep tabs on the output regardless, and work with your fellow engineers if you notice the power generation is steadily decreasing. But there is some grumpy noises to keep out for. If you hear anything like this, it means the engine's losing some power. The engine also has an emergency shutdown protocol where if the pressure difference becomes too great, it'll turn off forcefully, where it'll have some emergency lights on it. Hard to do, but it can happen, so just, there's also that. We're done with TEG stuff, I swear. Alright, so, cool video, but I just want to set this thing up. Alright, fine. A basic TEG setup looks like this. Find the charcoal, load it all into your hand, fill the furnaces with them, turn them on. Then take a plasma can, hook it onto the hot loop connector port with a wrench. Turn the right valve so the gas passes through the furnaces, the TEG, and then back into the loop. Then take another plasma can, hook it to the cold loop connector port. Turn the proper valves so it sends the gas into space, through the cold blower, and then back. Finally, make sure that the smess is set and outputting power to the station. The before described strategy is all that you'll need to satisfy an engine for a round to go by without much power trouble. All this going forward is for if you want some comical amounts of power generation or to make big bucks at the PTL. Or to just say that you did it. That's a lot of Space Station 13 after all. To start, let's get the basic idea of what you want to go for when working with the TEG. Let's talk about thermal energy. In the TEG, the two things that contribute to the energy generated by the TEG is the difference in temperature between the two gases and the heat capacity of the gases. As for temperature difference, the basic idea of keep hot hot and keep cold cold still holds true. The greater the difference, the better. However, as for heat capacity, there's a few more factors. In real-world science, heat capacity is how much heat energy is required to heat up a substance. In-game and for TEG purposes, heat capacity is calculated by the amount of gas in a space, in this case the blowers, times the specific heat of the gas. The amount of gas is just the physical amount of gas, better represented by the mole count of a gas than the pressure or temperature. And the specific heat of the gases can be seen in this table. These two variables are, at a minimum, what you'll need to keep in mind when going for big values in the TEG. Now, obviously, it'll get more nuanced than that, but anything to increase these two things will be a boon for your power generation and should always be kept in mind. Let's talk about a few modifications you can make to the TEG. One of the simpler modifications you can make is adding a brand new thermocouple in the center of the TEG. Screwdriver, wire cutter, and crowbar the thermocouple out of the TEG to remove it. A good thermocouple should have a high electrical conductivity, but be thermally insulative. Clarentine and Filbrith are a few good options. Whatever mineral you choose, you can either use the arc electroplater to plate the thermocouple you have, or use a nano refinery to make a new one. To insert a new one, click on the TEG with it in hand, add wiring, wire cutters to affix them in, then screwdriver it all together. The blowers have a few modifications you can make to them to make them work more efficiently. Blowers work by trying to equal the outlet valve's pressure to the inlet valve's pressure. The blowers draw directly from the room's APC and require more power and effort the more gas you need to push through them. The first modification you can make is simply adding a new lubricant to the blowers. By adding a superior lubricant to what is already in there, it can pull gas more efficiently and it takes less power drain to do so. At the start, blowers already have oil as a lubricant inside them. To remove this lubricant, first use a screwdriver on the blower to open up the maintenance hatch, then a wrench to open the drain cap and drain the lubricant inside. You can add up to 200 units of any lubricant or 2 beakers for scientific purposes. To add it, first make sure the drain caps are closed or lube will just slide right through. Then click the blower till all your lube is poured in. Then screwdriver it up to close the hatch. There's a few options for what may be defined as a superior lube, just about any of them needing to be made in a chemistry lab. Space lube and organic super lubricant both have superior lubrication on the grounds that they're true lubes, unlike the poser lube that oil is. If you want to get interesting with your setups, cryostylane and pyroxium are chemicals that excel at cooling and heating respectively. You can actually use these as added forces of heating or cooling inside the blowers themselves. Whatever you use, keep in mind lubricants will only help your engine move gas easier, especially when messing with the next setting. Blower manual override. When this is on, as opposed to just intaking gas so as to keep pressure relatively stable along the pipes, this forces the blower to try to get the outlet pressure to however high you set it. It'll do this by pulling more gas from the inlet side, resulting in a greatly increased heat capacity in the blowers. It's not all sunshine and roses, of course. Pulling in too much can result in a vacuum in the inlet, which will force some serious effort on your blowers and greatly increase power requirements. In general, a basic setting I like to use is to keep the hot loops blower manual override slightly lower than the inlet pressure, and the cold loops blower to be equal to or higher than the inlet valve. You can even use MetComp to automatically set the manual override pressure amount. I'm going to be real with you and say that I'm not an ultra TEG expert, and a lot of this stuff gets into the thick weeds of Atmos code and the sick gnomes that craft it. Experiment, figure some stuff out for yourself. Another thing basically essential for any half-decent output is reinforcing the pipes. At a base level, a pipe is rated to handle around 1500 kilopascals, known as its fatigue pressure. Past that, pipes start having a chance to burst, emptying its likely extremely spicy contents into the air and allowing more gas in the pipes to exit. There exists a few options for reinforcing the pipes to raise their fatigue pressure. First is using material sheets to fit the pipes with in order to multiply their pressure resistance. Using 5 material sheets on a pipe with a welding tool in the other hand, you multiply the pipe's fatigue pressure by the material's density squared. For example, steel has a density of 4, so 4 squared or 16. 16 times 1500 is 240,000 kilopascals max pressure. There's a few ways to make material sheets out of new materials, but the easiest is simply taking an ore and sticking it into the sheet extruder in the refinery for 10 sheets per piece of ore. You can also increase the fatigue pressure by building a wall on top of a pipe, multiplying it by 5 times the density of the sheet used on the wall, or 10 times if it's reinforced sheets. This has the downside of putting a fat-ass wall in your way, but it's an option that's there. With reinforced steel sheet, you can increase a pipe's fatigue pressure to 600,000 kilopascals, which is pretty good. The last and most effective way of reinforcement is graphene hardening compound, or GHC. GHC is a chemical that can be applied to pipes to increase their fatigue pressure by a factor of 2 to the power of units applied to the pipe. In other words, if you put 10 units of GHC on a pipe, it's 2 to the power of 10, or 1024, and 1500 times 1024 is 1,536,000 kilopascal. No, that's not right. 15,360,000 kilopascal. Stupidly huge results, but isn't really an option unless the research department is willing to play ball with chemistry. Just a note, the bonus from GHC caps at 1 billion, so don't go past 44 units of GHC. But if you are, get your scientist a damn grant, or just run a real power plant at this point. I've debated on how much to explain about the mechanics of toxins research and gas interactions. Honestly, I don't know how much I could tell you. All that I'll do here is do my best to give you the basics. At a base level, you'll need plasma to light on fire and maintain a fire, and oxygen to support the combustion. Mixes vary from engineer to engineer, but generally know that the higher the oxygen to plasma ratio is, the hotter but shorter it will burn. Oxygen turns into CO2 when heated for a long period of time, and CO2 is very non-reactive. Of course, it's not that simple. It never is. You have options to mitigate CO2 growth in your burns. First is, quote-unquote, methane. So, methane takes CO2 and turns it into plasma, and doesn't inhibit combustion. If you want to add some methane to your mix, you can either buy it from a certain trader in QM, or make methane with an air scrubber and a dark room and some friends and no shame. You gotta do what you gotta do after all. The alternative is Agent B, a rare product sourced from Mallet's beta, which is a very rare version of Mallet's. Every piece of Mallet's beta can be heated up until they burst open, releasing some oxygen Mallet's beta into the air. Agent B turns CO2 back into O2 and greatly increases the maximum temperature of a burn. Oh, and there's another bit of tech to let you know about. So, you know how thermal energy is built in the thermocouple by the two differences in temperature mixing, right? You can use this for your burn chamber as well, if you have a high enough temperature burn and open the vents. The chamber in space meeting makes a stupid amount of thermal energy. Now, obviously, space is the absence of anything, so nothing gets hotter there. But you'll see the outer edge of your chamber start to burn white, maybe even blue hot. Regardless of what you cook with, it's generally advised to keep a constant low input of the mix so as to keep the burn fueled while not using up all your gas at once. Also keep in mind there's ways to tailor what the 1 or 2 cans you have hooked up in there have in them. Take note of any surrounding pipes that are designed to let canisters mix their gases together, or just make your own with a pipe dispenser if you'd rather. Now, all this is assuming you're doing this in the burn chamber. You wouldn't be doing all this in the pipes, right? I mean, you could. You wouldn't even have to bother with transferring the heat, as all the heat would just be in the pipes. Power generation's theoretically insane, but pipes couldn't handle any pressure like that. Probably not. I can't really cover all the nuances here. Even with all this here, it's not uncommon something might slip the mind, or you might not consider some wayward factor, or consider the ideal gas law well enough. If there's some questions you still have, there are people smarter and way more experienced than me who I had to rely on to do this guide any sort of justice. Ask questions in the Discord and experiment, and just maybe, you can get some real stupid power. Or die in a plasma fire, whatever's more fun for you.
I give it a week before this is entirely outdated.